Problem 20 first asks us to draw the cosine of x function and then secondarily draw the sine of 2x function. I drew these out real quickly for you. The cosine is in red. That is a simple cosine curve. Then the purple curve is our sine 2 of x curve. That is a normal sine curve, except that its frequency is double. So our peaks are happening twice as frequently as in a normal sine curve. Part C is asking us to find the area bound between these two curves. So if curve A is our red cosine curve and curve B is our sine curve below, purple sine curve, we need to essentially find the green highlighted areas in each section. So this isn't necessarily a difficult problem, but it is a long problem, because what we're going to have to do is, instead of just finding the area equation based on some integral, we have to do 5 separate integrals for each of these separate green areas. So first and foremost, we need to find the intercepts between these curves to break up this integral. And we can do that by setting each equation equal to each other. So we have cosine of x equals sine of 2x. To solve this, we're going to need to remember one of our trig rules. So if we use the double angle rule, we know that sine of 2 of x is also equal to 2 sine of x times cosine of x. And if we substitute this in here, we'll have cosine of x equals 2 sine of x cosine of x. And now if we bring cosine out to the other side, we're going to get 0 equals 2 sine of x cosine of x minus cosine of x. We can factor out the cosine, and we'll get 2 sine of x minus 1 times cosine of x, all equals 0. So we need to solve for x at 2 different equations. We have cosine of x equals 0, and we have 2 sine of x minus 1 equals 0. I have up here a unit circle written out. I would always, if you don't know this or have it memorized, take a time to just copy it down. Just write it on the side of your piece of paper or scribble it down if you need to. It's better to not get confused and not pick the wrong numbers when you're trying to figure out what angles are what angles. So we know cosine equals 0 at 2 different spots, 2 different unique spots, pi over 2 and 3 pi over 2. And if you kept going to 5 pi over 2, you've essentially continued all the way around the circle back to pi over 2. So we can exclude that. This one is an extra step. We just need to solve for sine of x equals 1/2 over 2. And then we need to find where sine equals 1/2 over 2. So for that, it's going to be any place where you have a positive pi over 2. That is going to happen at pi over 6 and 5 pi over 6. So now we have 4 points where this equation intercepts. And we can annotate that up here if you so choose. This is going to be pi, I'll use a different color. Let's use red or orange maybe. We have pi over 6 is this intercept point right here. This intercept point right here is going to be pi over 2. Our next intercept point is right here, which is going to be 5 pi over 6. And then this last intercept point is just 3 pi over 2. And then we can use as our other bounds that are not intercepts, 0 as our leftmost bound, and then 2 pi as our rightmost bound. So now we basically need 5 separate integrals that are finding the area from each of these 5 unique distances. Okay, so I have gone ahead and set up the integral. So as you can see, each of our different 5 integrals we've set up covers each of the segments. We have 0 to pi over 6, pi over 6 to pi over 2, pi over 2 to 5 pi over 6, 5 pi over 6 to 3 pi over 2, and then 3 pi over 2 to 2 pi. And now just make sure when you're setting up big problems like this that in each segment you have the correct function on top. So as you can see for our first segment, cosine is our top function, so cosine is going to be the first function in our integral. And then minus sine 2 of x is underneath. And then it's the inverse for the next one because the sine function is greater than the cosine function for the second segment, and so on and so forth. So take a moment and solve that integral if you haven't already. Okay, this is my work done out. I've come to an answer of area equals 5. Make sure you go slowly as you do problems like this because it's easy to get confused with your trig functions. I know I did about a dozen times while doing this myself. And of course, if you find an error in my work, feel free to leave a comment and I'll go back and take a look at it. But the best thing with these problems is just to go slow because a lot of C's and S's can be confusing when you're taking integrals and it's flipping back and forth with trig functions. All right, thank you.